Welcome to this explainer. Let's just dive right in and completely rethink how we teach basic math operations. For so long, mathematics instruction has relied heavily on memorizing rules and facts. But today, we're going to look at the research and explore how to build genuine, lasting operation sense in a student's mind. We really want to move away from rigid procedures and instead focus on helping learners connect different meanings, interpretations, and real-world relationships directly to addition and subtraction.
I want to start us off with a bit of a provocative question to challenge a really common assumption. Is addition always just putting things together? And by the same token, is subtraction always just taking away? In most curricula, the overwhelming emphasis gets placed on these super simple actions. But the research reveals that these become the default, highly limited definitions of addition and subtraction in a kid's mind. The reality is actually much more complex and, honestly, a lot more interesting.
Here is our roadmap for today's explainer. We'll start with building true operation sense, break down change problem structures, look at part whole and compare problems, tap into the power of context, and finally, wrap things up with model-based tools.
All right, Section 1, Building True Operation Sense, Moving Beyond Rote Memorization. To really grasp this, we look to the National Research Council. They anchor how we should view these operations with 4 big ideas. Notice the absolutely foundational point here. Addition and subtraction are intimately connected. Addition simply names the whole in terms of the parts, while subtraction names a missing part. It's really that simple. And this structure holds true whether a student is working with whole numbers, fractions, or decimals. Plus, using models to solve contextual problems isn't just some fun add-on activity. It's literally fundamental to figuring out what operation is even involved, giving true meaning to number sentences.
Moving to Section 2, Change Problem Structures. Time to deconstruct the math. It's honestly fascinating how we can break broad operations down into specific physical problem structures based on the kinds of relationships involved. Let's look at change problems. These are situations where a physical action takes place over time. They operate using 3 distinct moving parts: a start amount, a change action that alters that amount, and a result. So, for example, Sandra has 8 pennies, George gives her 4 more, boom, resulting in 12 pennies. But here's where it gets interesting. We have to understand the difference between joining and separating within these change problems. In a join or add to problem, the final result represents the whole or the largest amount. But in a separate or take from problem, it's the start amount that is the whole. What's wild here is where students actually stumble. While both involve an action, students almost always struggle most when the start or change amounts are the unknown variables. Why? Well, think about it. If the problem says Sandra had some pennies and George gave her 4, a kid trying to model this physically has absolutely no idea how many blocks to even put down to begin with.
Which brings us to Section 3, part whole, and compare. Let's look at situations that don't have a physical action.
Imagine a scenario like this. George has 4 pennies and 8 nickels. How many coins does he have? Notice there is no physical action of giving or taking away happening here at all. The challenge for the learner shifts entirely to mental organization. They have to conceptually combine those distinct parts, the pennies and the nickels, into one single whole right in their mind. These 2 non-action structures actually place vastly different cognitive demands on a student. In part whole, there isn't really a meaningful distinction between the 2 parts. They are simply components of a single total. But compare problems, totally different beast. Here, we are comparing 2 entirely distinct, separate quantities. And what makes compare problems incredibly tricky is that the third amount, the actual difference between them, doesn't physically exist. It's a highly abstract concept for a young learner to grasp. And speaking of tricky concepts, here's a surprising fact. You know that simple phrase, how many more? It pops up in comparison problems all the time. Well, it frequently confuses students into adding instead of finding the difference. Their brain hears the word more, and it just triggers an addition reflex, totally bypassing logical reasoning. This right here is exactly why we need to build deep operation sense rather than just teaching kids to hunt for keywords.
Let's pivot to Section 4, the power of context. This is all about making math meaningful.
We absolutely must abandon naked numbers. When students are just staring at naked equations or sterile story problems, they just focus on churning out an answer as quickly as humanly possible. But meaningful context problems, they are designed to anticipate how children actually model the real world. We need scenarios that kids actually care about, situations that make the math feel necessary and logical.
So how do we build that context? You draw from recent classroom events, field trips, or tie the math directly into great children's literature. Furthermore, by keeping the language structured, using a really simple noun-verb word order, and replacing confusing generic pronouns with specific names, we support all learners. This is incredibly important for English language learners and students with disabilities. It lowers the linguistic cognitive load, so they can focus all their mental energy entirely on the mathematical relationships.
All right, our final section, number 5, using model-based tools, helping them hold the math right in their hands.
We want to logically walk students through a very specific progression here, moving from concrete physical objects to semi-concrete visual models. It's a journey from things they can touch to things they can draw, all the way to abstract representations of distance and magnitude. Starting with physical blocks, like base 10 materials. There is a vital strategy to employ here. Keeping the parts visually separate in different piles is essential. Why? Because students need to be able to physically reflect on the action that just occurred. They need to look down and say, okay, these 35 blocks are what I started with, and these 55 blocks over here are what I just added. If they just mush everything together immediately, the relationship between the parts and the whole is completely lost.
Next up in the progression, we move to bar diagrams, also known as tape or strip diagrams. These are heavily utilized in Japanese curricula and Singapore mathematics, and for good reason. They brilliantly allow students to translate a complex word problem into a clean, relational visual. They literally generate a meaning-making space that explicitly shows the connections and relationships between the quantities in a problem context, way before any calculation even begins.
And finally, we arrive at number lines. Now, while number lines are incredibly powerful tools, we have to recognize that they require a massive conceptual leap for younger students. Up until now, students have been counting distinct physical objects. A number line requires them to suddenly understand continuous length, where the unit is actually the space between the numbers, not the hash marks themselves. It's a vital shift, but one that definitely needs careful, guided instruction. I'm going to leave you with this final, provocative thought. As you look at the tasks you give your learners, ask yourself, are your math problems simply asking for a quick answer, or are they asking for an explanation? Because when we challenge students to use words, pictures, and models to justify their reasoning, we aren't just teaching them to calculate. We are inspiring them to build true, lasting operation sense. Thanks for joining me on this explainer, and keep exploring.